Everything is okay? Full. Good afternoon. Welcome to course Thermodynamics of Materials. We are discussing the Gibbs Phase Rule, and we are discussing, we have taken up already the 12 examples of demonstrating the Gibbs Phase Rule, finding the degrees of freedom and showing by fixing a number of variables. F means F is actual degree of freedom. F number of variables, the state of the system, okay. The state of the system can be completely defined in terms of temperature, pressure, and composition of each phase at equilibrium. This was actually, we actually finished 10 examples already. So today we will take up the 11th example. So this is 11th example is what I write. This is a purely a condensed phase chemical reaction, 2FeO solid plus silica solid going to 2FeO.SiO2 solid. Call it equation 1. Okay, and this is actually you may consider this also as Fe2SiO4 alternatively. Okay, so this is the reaction. We will apply the Gibbs Phase Rule. So we write as we do, F is C minus P plus 2. Next job is, remember these two figures are not relevant to this discussion, this example. This will be relevant to example 12, the next one. And this is the actually construction of stability diagram. That is the next topic or subtopic, okay, under Gibbs Phase Rule. So that is the next one, okay, that will be taken up after we have completed the examples, 2 of the examples, then we will take up this. So this is much later. So this consider this will be taken up when time comes actually, and when time will be appropriate for discussion of this diagram. So I will let you know. So for the time being, ignore these figures, okay, for these examples. F is C minus P plus 2. You may have a sketch always, you know. This is your system, this is the pressure P, this is the temperature T, and you have 3 solids, okay. FeO solid, SiO2 solid, and 2FeO SiO2 solid. This is under equilibrium, and it is what should I write actually, figure 11. This is only one figure for this. So this now C is what? Giving this, C is, as you know, number of elements. If you go by this number of elements, but this time I particularly note this number of stoichiometric restriction, the one that I gave you as an alternative definition of C is number of elements. So far we have not considered this number of stoichiometric restriction because that was not there. But this case we will actually come across stoichiometric restriction on the composition of each phase. So let me include that one, number of stoichiometric Also, I will show you the alternative definition or the primary definition of C is actually number of, in terms of number of species. Definition of C in terms of number of species, that definition we'll also consider, and we'll reconcile these two. So let me write number of stoichiometric. Here let us give fencing here. This is for different topic, okay? So, right, very good. Stoichiometric restrictions. On the composition of each phase. In the composition of each phase. What is this? See, I write number of elements is 3 minus 1 restriction is 2. What are the number of elements? Elements 3. Elements are who are here? Fe, Si, O. 3 elements, so 3, but there is a restriction, so it becomes C is 2. Alternatively, C is what? Definition in terms of number of species. It is number of elements and the number of species. By the way, before this, before I take this alternative definition and actually corroborate this one, okay, this value, corroborate, okay, this is actually substantiate this value. So I take up this little later, but before this, why it is there is a stoichiometric restriction? See, follow this. This is the restriction. Stoichiometric restriction is what? Restriction. What? NO is twice NSI plus NFE. This is the restriction. I tell you what, if you consider this restriction, it applies to each phase. I will show you how NO is for FeO. For FeO, I show you see, it applies for FeO. The phase FeO, phase SiO2, phase 2FeO SiO2, each of them. This restriction. FeO, what is the NO? NO is how many? 1. What is the NSI? None. 0. And what is the NFE? Is 1. So this satisfied. Similarly, another one you take up FeO phase, SiO2 phase. You try again. NO how many? 2. NSI how many? 1. And NFE how many? Is 0. So you see, 2 is 2 times 1 plus 0. Yeah, in the second case. In the first case, NO is 1, NSI is 0, so this is 0. 1 is, NFE is 1. So 1 is 1. So satisfied. Similarly, you can try yourself. This is also satisfied. So this restriction applies. I tell you what, when you will actually come across this type of situation, another example I gave you, the first example rather, when I was introducing this one, calcium carbonate goes to calcium oxide plus carbon dioxide. So this is another one. When you come across this, I tell you, see, another example I gave you, remember, calcium oxide plus carbon dioxide goes to calcium carbonate. So how to identify this situation? When you see all participating species are in a bound form. In a bound form, say calcium oxide, no free oxygen, no, or say none of them, neither oxygen nor calcium nor carbon, not free, always bound, then you understand you are under this situation of stoichiometric restriction, and you apply this. In that case, C will not be equal to number of elements. Okay, or it will be number of elements minus number of restrictions, like this. Okay, so this is this. These are just the situations. Okay, so previous cases always you will see there is say free oxygen or other things. Okay, there is carbon, oxygen, etc. etc. Metal, AM class O2 is MO2, AM is free. So, but none is free. None is free. So always all species are in bound form. So in that case, restriction comes, and this type of restriction. And also you may write here, actually you can check here, say 2FeO.SiO2 phase, if you are interested, 2FeO.SiO2. Here also same thing. You tell me how many, do yourself, NO is how many? How many NO? 2FeO. 2FeO is 2O and SiO2 2O, 4O. NO is 4. How many NSi? Is 1. How many Fe? NFe is how many? 2. You substitute this here. So 4 is 4, NO is 4, is 2 times NSi is 1 plus NFe is 2. Yes, it satisfies. So all phases are satisfied. So you are satisfied, there is a restriction. This is the restriction. Actually, another thing I tell you, why this happens, as if you are here, you are pretending that elements are components, but these elements actually are, you consider them elements, but they are actually bound by a relation. And when there is a relation, means restriction. Remember previously we actually always take away this number of restriction from the number of elements to get the number of components. Anyway, this was discussed at length last time. So this is what C is 2. Alternatively, tell me, alternatively you can get this. What is C? C is number of, in terms of species, number of species minus number of independent reaction equilibrium. Independent reaction equilibrium. How many it is? Number of species, how many? 1, 2, 3. 3 species minus how many reaction? 1 reaction 1 is 2. So reconciled. We have the same result, we are satisfied, fully satisfied. So start here. C is 2. How many phases? 3 solids. They are pure solids. So 3 phases plus 2 is 1. 1. So call it, let us fix it. Fix it as, okay, 1 is what should I write here? 1. Fix it as pressure. And this pressure. We are fixing this. Okay, 1 degree of freedom at our disposal. So fix this as pressure, not temperature. Okay. So this, given this pressure, maybe 1 atmosphere, maybe, okay, or maybe other values. So by the way, what is the P? P is 3 while, right here, P is 3 while, P is 3, the phases, 3 solid phases. Which are pure? So this is a P here. So it is on P. Given this, now start doing this. Start here. Delta G. Since pressure, we can choose any value. Freedom means freedom. Freedom is freedom. It is not necessarily 1 atmosphere. It can be 2 atmosphere. It can be 0.5 atmosphere. So whatever the pressure, suppose it is 1 atmosphere, then it is, I consider this, that I consider that it is any arbitrary value, any freely matter of choice chosen value. So say it's a pressure which is not exactly 1 atmosphere, or say it is different from 1 atmosphere. So I write delta G1, but you have to accept that delta G1 is delta G01. Why? They are, strictly speaking, they are not same, because pressure under standard state 1 atmosphere pressure is the standardized pressure, is the is the pressure that is fixed for the standard state, specified for the standard state. But this is any value, say 2 atmosphere, so it is delta G, then it is non-standard state, delta G. So but effect of pressure on condensed phases is negligible for small deviation from 1 atmosphere. So in that case, this may be close to this. Or even if you consider the mathematically, it will be involved. The effect of pressure have been studied, and we have already studied. Is dg is VdP. How pressure actually changes the free energy dg through dg is VdP. That can be included, and no problem. No problem. Only mathematically it will be more involved unnecessarily. Our understanding, main understanding is this delta G is this delta G01 is close to this, since effect of pressure is small or negligible. So is what delta G01 is what you tell me is what minus, oh wait a bit, is A plus BT. This you know, always you know, A plus BT form. A is delta H0 as you know, and B is minus delta H0. These two are known quantity from where? Data book. Okay. So given this, very good. And also you may, since this is a combination reaction, delta H0 is also negative. This is negative. Delta H0 is also negative, and this. Okay. So anyway, the negative. Okay. So delta H0 is this one. Okay. So A plus BT is what? Should I write 0 is at equilibrium? 0 is, because this is under equilibrium. So 0 is delta G. Is delta G0 is A plus BT, or T is what? T is minus A by B. A by B, here A is negative. Okay, so negative actually these values actually, and I don't have to give this. What is B? B is minus delta H0, and A is delta H0. A is delta H0, B, T is minus A by B. So this is now for this pressure giving temperature is formed. So we actually found a temperature. This temperature will be positive because I tell you what, B is minus delta H0, A is, this is a combination reaction, so A is negative, then A is negative, B is positive. B is minus delta H0, B is positive. B is positive, A is negative, so everything. Why B is positive? B is minus delta H0, means delta H0 is negative. That means these three solids, this is one solid, Fe2SiO4, and there are two solids on the reactant. So they have more entropy, three molecules, if I may say, 3 molecules or 3 moles. Here is 1 mole of Fe2SiO4. So we expect this delta H0 is product entropy minus reactant entropy. There are 2 species on the reactant, so reactant entropies are greater. So delta H0 is negative, and B is incidentally is minus delta H0. So B is positive. So B is positive, A is negative, negative, positive. Temperature should be positive, and is fine. So temperature is found. What else remains? How to define the system at equilibrium? Okay, by this what? Then composition of each phase. What is the composition, right? Composition. Take pressure known because you have fixed yourself. Yeah, you know best. You have fixed what value it is. So it is well known, and T is now found, is known. So composition. So if three phases are there, you just keep on writing. XaPO is pure one, pure solid, pure solid one. Likewise, XaSiO2 is 1, XaPO. I'm sorry, 2FeO dot SiO2 is 1. So composition of each phase is known, temperature is known, pressure is known. So we are satisfied. So demonstration of the degrees of the Gibbs phase rule. So let us write this. So what is this? Hence by so you may write hence by fixing F, which is nothing but by fixing the F variables, F which is 1, a variable, the system is fully defined. System is fully defined in terms of temperature, pressure, and composition of each phase. At equilibrium. So there it ends. So this problem is over. This problem is over. So no problem. So start to a problem 12. So I'm sorry, example 12, not problem. 12 examples of demonstrating the Gibbs phase rule. So 11th over, last one. This is what? Binary phase diagram. Wait a bit. This is phase diagram. Last one is phase diagram. This one. Phase diagram. This topic is phase diagram. Binary. Three cases we will consider. Three cases we will consider. I will give it one by one. First case is coming to this liquid phase. Before this, I will take up this one. First case is L. That is fine. Very good. And I will start with this. F is C minus P plus 2. First of all, before this, you know very well, this is a eutectic diagram. Binary eutectic diagram with no solid solubility. So completely pure. So this is, see, T is plotted against XP. This you know, but still I should actually repeat some statements that I have. Also I should give some introduction of this. So temperature is plotted against XP mole fraction. This is 0, XB is 0, XB is 1 into pure A, pure B, XB going temperature. This is binary. This is this is liquid plus A, solid. That side is liquid plus B, solid, and this is the liquid phase, and okay, and this is actually, this is the eutectic temperature. TE is the eutectic temperature and E is the eutectic point. I'll mention this. E is the eutectic point, T is the eutectic temperature on the this line, this temperature. TMA is the melting point of A, TMB is the melting point of B. This is level A, B, C, D, E. Okay, and this I have already explained. This is A solid plus B solid. We call it eutectic mixture of the solid. So this is all known, nothing new. What else? Okay, this is pure A, pure B, equilibrium binary phase diagram. What else? Okay, and this is the liquid phase. This is the liquid phase. Yes, one important issue here, as far as Gibbs phase rule is concerned, and there are much confusion about this, but you note this. This diagram is drawn with the understanding, with the consideration that pressure, for a given pressure, this diagram is drawn. That is not mentioned in books often, and students also are not actually much concerned about that, and they also actually didn't notice that the pressure is not mentioned. It is understood, but when this phase rule is, when you actually specify any pressure, means you are applying a freedom. That will be very important. So P is fixed on the top of the diagram, which is missed in books, in textbooks. P is fixed. What value it is? Fixed any value. P is fixed. This is freedom. It can be 2 atmosphere. It can be 1 atmosphere. It can be below 1. So for the timing, I consider it is 1 atmosphere. Say it can be 2, it can be 3, it can be 10, 100. So for why 1 atmosphere is very popular? Because the melting point TMA corresponding to 1 atmosphere total pressure is called the normal melting point. And similarly, normal melting point of A and normal melting point of B. If it is not 1, it is no longer normal melting point. It is actually just any ordinary melting point. Any melting point. So this, and effect of, again I repeat, sometimes students actually avoid considering this, thinking this. They consider the effect of pressure is minimal on the condensed phase. This is a purely condensed phase situation, solid and liquid. Effect of pressure is small, so they ignore. But in principle, you should not. Degree of freedom, this number is purely mathematical calculation. Theoretically, you should show that it should be consistent with the Gibbs phase rule. It is an equilibrium diagram after all. We will apply the Gibbs phase rule. So mathematically show that it is actually following the Gibbs phase rule, in compliance with the Gibbs phase rule, in agreement, total agreement. How to do that? So don't consider that it is this. Okay. In fact, what will happen? Suppose this is 1 atmosphere diagram. If it is 10, what will happen? You know what is the reference? Effect of pressure on melting point. Single component phase equilibrium, I taught you. Clausius equation, Clausius-Clapeyron equation, okay, or Clausius equation. So there, effect of pressure. If the normal cases, if pressure increases, melting point increases. So melting point will not be here. Suppose it is 1 atmosphere here, the normal melting point, which we call, for 10 atmosphere, it will be slightly rise. It will rise, and that will also rise. Looks good. Everything is okay? No problem? No. Clear? Everything is visible? Thank you. So it will rise. Only thing also for small change in pressure, say 1 atmosphere to 1.2 atmosphere, 1.3 atmosphere, the change will be negligible. Even 2 atmosphere, it will be negligible. But when it is 10 atmosphere, For 100 atmosphere, of course this will change. These points will change. This will rise, this will rise. The effective temperature will change. So why should we ignore? What's the purpose of ignoring? Why are you actually keeping yourself in the dark? Why are you unnecessarily taking risk? There is no compulsion of considering any assuming or putting any condition. Effect of pressure on high pressure. I also give you an example. The vapor pressure changes, etc. Zinc, some assignment problem. So why unnecessary? There is no need to consider that it is 1 atmosphere or pressure has no effect. Some books say students, teachers maybe AP C minus P plus 1 in the present case. That is very bad way of understanding this one. They're right that for phase diagram means tacitly means which deals with condensed phases AP C minus P plus 1. Because pressure has no pressure, they don't consider. But it is much better to say that no. Why should we not? Gibbs has not said that. That I have two rules. One is AP C minus P plus 2, another is AP C minus P plus 1 for metallurgical student. Gibbs didn't say this. For metallurgy, one student told me or asked me one day, it is for metallurgy or non-metallurgy? Gibbs phase rule. No, metallurgy means condensed phase. Condensed phase means the effect of pressure. Pressure is not there. Pressure has no importance, no relevance. So AP C minus P plus 1. Then they try to explain easily. But it will be equally easily you can explain if you consider that it is for a given pressure. In fact, it is for a given pressure. If it is a normal melting point, of course the pressure is considered as 1 atmosphere without any compulsion because I have considered 1. Or I may consider change it also as well. So this part is I have mentioned here. This I will do in stability diagram construction in subsequent cases also. If temperature is fixed, I will write on the top temperature is fixed. Similarly, here pressure is fixed, 1 atmosphere. Now move on. That means 1 degree of freedom is already applied. This is one very important thing, and you will understand this. Okay. F is C minus P plus 2. So what I tell you, let me write this. How many it is coming? F is C minus P plus 2. C is how many? It is a binary system, AB. So I will write that, but I am writing 2. Value is 2. Since liquid phase, this liquid phase, see what degree of freedom for the liquid phase. This is the liquid phase zone. The liquid phase, what is the degree of freedom? Apply the Gibbs phase rule on the liquid phase at equilibrium. This is equilibrium diagram. Later on, I will consider liquid plus A solid, and still later, third case, liquid plus A solid plus B solid, like this. So liquid phase, apply the degrees of Gibbs phase rule and find the degrees of freedom. C is 2 phase. See liquid phase alone 1 plus 2 is how many? Is 3. 3. Actually, right here, why C is 2? C is 2. Why? 2 components, 2 elements here. AB. C is 2 AB. AB system, binary. And P is what? Liquid phase alone. 1 liquid phase. So this is 3. Of these 3, pressure is already this. So this, I tell you what. C AP is 3. 3 degrees of freedom means 3 you must specify. You have the liberty of specifying. You have the freedom of specifying. Finally, you have to specify temperature, pressure, and composition of each phase. That is final. So it is a liberty. Now, 1 liberty, 1 freedom is already used in terms of pressure is fixed. So 1 gone. 2 remaining. Which are these 2? I tell you what? Temperature and Composition means mole fraction of B. Mole fraction of B of the liquid phase. So 2 degrees of freedom. So 2 degrees of freedom, when 2 degrees of freedom means, remember I said 2 degrees of freedom corresponds to 2-dimensional geometry. 2-dimensional representation means area, surface. So no surprise here that liquid is spread over an area. That's here. See, area. This when you can do this one, this way, this means 2 dimension, 2 degrees of freedom. If this stability spread over a surface or a region or domain, etc., 2 on the 2 dimension, so it is 2 degrees of freedom. So liquid has a 2 degrees of freedom, while actually 3, but 1 already consumed, so remaining 2. That's why it shows this way, 2 degrees of freedom. Okay, but this actually I will tell you, liquid phase. Okay, because there are some interesting situations, so we try to. Okay, very good. So let us jot down a few lines. Since the phase diagram what is the figure 12? That is figure 12 is drawn after already applying applying 1 degree of freedom, 1 degree of freedom, 1 degree of freedom, 1 degree of freedom, 1 DOF. Okay, in which form? In the form of pressure, fixing pressure. So 1 degree from in the form of fixing pressure the remaining available already applying 1 degree of freedom, available degree of freedom is 3 minus 1 is 2 is 2 degrees of freedom, which are what? Temperature and XB, temperature and composition, pressure, temperature and composition, all known, T and XB. So you have to elevate it. Note in passing when P is fixed at 1 atmosphere, TMA, yeah, this point, TM melting point, TMA, melting point of A, TMA is the normal melting point of A, is the normal melting point of A. And similarly, TMB would be normal melting point of B. Okay, but this is that's name. Okay, name means when it is 1 atmosphere. If it is not, then no problem. But we will apply the degrees of freedom. The diagram will slightly, though slightly, little bit, but all the same it will change. You change the pressure and melting point will not change, then it will violate the Clausius-Clapeyron equation. And that phase diagram, remember, recall that diagram. Should I, in fact, that's a good thing to recall. P versus T, effect of, this is the melting point. Single component system. Revisit, okay, brush up on your, okay, your memory, okay, brush up on that, okay, so just recall, this may not be so much inclined, sorry, I drew actually very nicely, but not bad. Solid, liquid, vapor. This is pressure temperature. Single component phase diagram. Is solid. What does it mean? This is a regular case. For water is an unusual case. So water, the line will be like this. Water will be lying like this. Okay? But all the same, there is a effect of pressure. You change the pressure. At this pressure, this is the melting point. You keep change the pressure, melting point changes. Does not change. This shows clearly shows. Remember this. So you change and similarly. So, but this steep, so effect is small. Large pressure change is required to have a measurable change in temperature, means melting point. Remember this, huh? So I am removing this. So recall this, and you will be very satisfied that it is good thing that we write. In fact, it is a practice we will write in subsequent phase diagrams where we will fix one variable, then draw. Fix first and then plot. And that time maybe temperature will fix. Sometimes we will fix pressure also, a partial pressure. We'll do this. So why not here also? Even you don't write, but you should understand, you should know inside your head, you should know full well that it is after applying 1 degree of freedom in the language of Gibbs Phase Rule. After applying 1 degree of freedom, this diagram is drawn. These equilibrium relations are obtained. These temperatures are obtained, these compositions are obtained after a certain value of pressure. Okay, James melting point is. So next, looking from a different, this is okay, 2 we have understood, temperature XB. Achha, by the way, temperature XB, okay, let me complete this. Looking from different viewpoint, I have already said, since it is spread over a two dimension with the dimension, from dimension you will also interpret. Since liquid is spread over, the liquid phase stability is spread over 2 dimensions, because it is area, surface, then it has a degree of freedom too. That is also another way of understanding very nicely. Okay, so this mathematically this, and these are the explanation temperature XP. I tell you what. Then okay, looking from a different viewpoint, the liquid phase is spread spread in two dimensions. In two dimensions. Hence, the degree of freedom for the liquid phase being 2 is apt, is correct, is suitable, is justified, is apt. Okay, very good. This is, I tell you another thing here that will be helpful also. If you follow this, I'll show you here. Maybe another. Maybe for contrast, see how you 2 degrees of freedom. See, consider this. Here it has. Oh no, it is. Here I am showing you. Just choose any temperature. From this side, this is temperature scale. Any temperature here. Any temperature. Okay, choose arbitrarily. This temperature means any arbitrarily. It can be above it, below it, arbitrary. So arbitrarily this point, temperature. One freedom. Or the second freedom. First freedom is here. Pressure. Temperature, arbitrarily. Composition. See composition. Since this with this temperature, composition can be here, can be anywhere here, this direction, or anywhere this direction, anything. Any composition. With this temperature, you see composition the x-axis. So this any value, freedom. Any means freedom. And here also any means freedom. If you argue that's this way, if you say freedom, but if I extend the freedom, then it will enter into the liquid plus A. Sir, liquid plus A, or here if you extend, it will be liquid plus B. It is no longer liquid, sir. Violates. Then freedom cannot be full freedom. Yes. Remember, over a zone you are applying this liquid phase, and you see mathematically, you remember mathematically limited freedom is full freedom. Limited freedom means what? You say here a composition is here from this to, for this temperature, in this composition. See, follow? In this composition. Then beyond this it will be 2-phase region, land into 2-phase, liquid plus A this side or liquid plus B. So then see, that means you are applying your freedom. This you are calling freedom from this point to this point. This is mathematically okay, no problem. Limited freedom is, it will be always limited. See, any zone always there is a boundary, always phase boundary. So limited freedom, but you remember this statement. Limited freedom is mathematically full freedom. Then what is not freedom? You don't have a bit of freedom. A speck of freedom. No freedom. Means what? You are fixed there. I'll show you in the next case. Or you already know. You have seen so many examples. This is the last example. So you have already seen. Fixed. Freedom means when there is no freedom, conclusively, because you cannot, can you choose? If you say, I choose, can you choose any other value? Just any value, very close to it also. No problem. Can you choose? No, you cannot, because it is tied there, fixed. When it is fixed means it is fixed by, you are not arbitrarily fixing it. It is already fixed for you, means you have no freedom. When it is a degree of freedom, you have seen many cases there previously. Okay, so triple point, as I said, triple point, you don't fix. A triple point, here, I have removed the figure, triple point, you cannot say this is pressure, this is temperature, solid, liquid, oh sorry, this is this part actually. I should show here. Pressure, temperature, solid, liquid, vapor. This is the triple point. This is all fixed for you. You are not fixing. If you say, if you argue, sir, I am fixing this pressure, I am fixing this temperature, although it is automatically fixed, still you argue that I am fixing. No, that then the acid test can fix any other. Since you are arbitrarily fixing, fix any other point, any, say oil. Say any, this is the temperature, this is the temperature. So any other temperature, sir, a little bit, even little bit, it lands, is this triple point destroyed. Three-phase meet, destroyed. So no freedom. You have no freedom. This is point. That's why it is a point. Any, say, no freedom. So it is, you are not choosing. You say it is automatically chosen and you are actually claiming that I have chosen it. No, that is utterly wrong and unthermodynamic. Okay, this is what. So this is a similar pressure. If you say I have fixed this pressure, so tell me if you fix this pressure. No, this is land into the solid stability zone. So this is called no freedom. Means a little bit of change, a little bit, little. Here you are moving from this point to this point. This limit, limited freedom though, admittedly, but here no freedom, no change. This side or that side, the tipping point is lost. It will land into two-phase, from three-phase to one-phase region, or maybe this. Okay, so this one, this way. So you cannot change a bit. So you should be careful. Limited freedom is also mathematically is a full freedom. Full freedom mathematically one freedom. Okay, because I can change. Can you propose? Can you fix a second value? Suppose you have say I fix P is 1 atmosphere. Can you fix any other value? 1.1. Yes, freedom, full freedom. Freedom is, there is freedom, limited. Say not say 1.5 because it will land into a different stability domain area. Okay, say different, say liquid plus B, etc. etc. So I have 1.1, no problem. But when it will be, when you have no choice, automatically it is fixed. Then if you try to change 1 to 1.1, then this liquid phase will be this is a very small change, even like this very small change. Then it will violate the original consideration. Okay, so remember this. So this is what I said. So limited change is allowed, but when you have no freedom, you cannot change even a little bit, small, to any small extent. You cannot change, cannot be changed. Okay, so this I have shown, maybe I have already shown, but maybe today since I discussed this point, so okay, is apt. So from two dimensions. Another way I tell you. So here also, other way also you can see. Suppose you fixed, you say, sir, I am removing this. I am removing this. Now, to make a room for writing this, some space. Say composition, sir. I am choosing composition, sir. Composition choose. This freely choose. Come here in the liquid. Oh, this will be better maybe. I will remove this also. I will remove this. This is my choice, sir. This composition. From here, composition my choice. That means if you drop this, yeah, this is your choice. Very good. It is your choice. Freedom. Okay. See, if you say, see here also, if you say, see, you can choose this, you can choose the other value like this, etc. Suppose you have chosen freely. Let me complete. Then temperature. What can be temperature? This is a composition. Temperature can be this value. Can be this value, lower, this temperature or this temperature or any other temperatures, intermediate temperatures, or above this, below this. But always there is a limit. Actually, you cannot choose a temperature here. Suppose here it is a line into two-phase region. That you should careful. But this is mathematical. This is actual demonstration. Mathematically, you see, this is 2 degrees of freedom. And always it will be limited. The freedom will be limited because also even simplest diagram, liquid, solid, and vapor, there is actually. I showed you. This is actually liquid, solid, liquid, vapor. So always actually there is a domain. See, beyond this point there is no solid. So you are discussing solid stability. So you must be here. So there is a limitation already inbuilt. Okay, that is no problem. So I say, you may note this, that limited, over a limited zone, your freedom means correct. This is actually freedom and mathematical freedom. So here also see temperature I have shown. Both ways you can have this. So this. But when in contrast, that you try to, this is try to understand. When there is no freedom, I'll tell you, I'll let you know in the next case. I've already number of times, when no means it is rigid there, that value, a little bit shape, decimal, say pressure is 1.01, no, will not be tolerated. Or temperature is say 500 Kelvin, you have found, okay, it is, and 5, you try to make it 500.01, it will not be accepted. But if you have freedom, 500.01, 501, 502, 800, 900, over a range, certain allowable range, you can. That is full freedom. That is mathematically correct. Okay. So I am removing this, and this actually I have keep this, but I hope it is better I remove this. I remove this unnecessarily. Okay. This okay. And this diagram, thank you. So let us take up case B. 3 cases B. So I remove this part is over. So I remove this. I remove this. I remove this. Okay. So far, well, start with this. This is start here. Case B. B, what we will consider? Liquid plus A. Liquid plus A. Okay, this one. It could have been liquid plus B also, but if I explain one case, similar case, the similar other case will be explained at the same time. Okay, so liquid plus A. Liquid phase plus time left.
1 hour gone. 1 hour left.
It's okay, thank you. Liquid phase plus A, solid. So simply what we call this as, in short, L plus A. Two-phase region like this one. This one, liquid plus A. One interesting thing I tell you beforehand. One interesting thing. Very interesting. You have a feeling that this liquid plus A is also spread over a two-dimension, over a region, two-dimension, check, two, like this. Yeah, as I said, this is two-dimension. See here, two-dimension here. No, that is very interesting. That is actually one thing. This is actually, sometimes students are misled. Okay, it looks like a two region, so should be 2 degrees of freedom, but you will see something different. So follow me. So liquid plus A, start again. Similarly, start. Second case, F is C minus P plus 2. Always never write C minus P plus 1. In some books it is written. No. If they mention that after specifying the pressure, applying the 1 degree of freedom in terms of fixing pressure, then what remains 1 less now, then it will be C minus P plus 1. But that should be mentioned. C minus, but it is better don't write it. Gibbs said F is C minus P plus 2. Gibbs said F is C minus P plus 2. Okay, I have written that. You must do. What are these? C is what? C, already I have told you, two component system. How many phases? Liquid phase and A solid, 2 phases. I am writing here for you. P is 2 while who are there? One liquid, one solid, which is A. So 2 phases. So degree of freedom is 2. So we have already is. So after fixing, since already I fixed one pressure, after fixing value of P, pressure, the remaining degree of, as P is fixed, the remaining degree of freedom is what? How many? 1 already, 2 total. 2 minus 1 is 1. 2 minus 1 is 1. 1 is there. What it can be? T, which is either T, it may be T or XP, any one of them, T or XP. Suppose, as this diagram, I tell you, in this diagram, I show you. Suppose you have fixed 1 degree of freedom, So follow this. T1 you have seen, T1, see T1, you have arbitrarily you have considered T1, this temperature. 1. It could be here, could be there, here say. Then see, at this temperature, what is the liquid composition? See, go this way and come down this. This one is not chosen by you. You have chosen temperature. But once the temperature is chosen and fixed, this composition here, XB1, is in a sense is automatically fixed. You cannot say you have fixed this and 2 degrees of freedom. You cannot say. It is automatically. Relative to this temperature, this is automatically. This is a matter of choice. Conversely, you may say, why I may choose, I may fix arbitrarily, independently composition, and that is possible. I say number is important. Which is that one who represents that number is a matter of choice. So you choose composition, any composition here, any say in this domain. So suppose you have chosen this. If you have chosen this composition, then go up. What is the temperature? See, it should be liquid. This is the liquid composition, and this should be the only temperature. This composition corresponds to this temperature. You cannot change it a bit. A speck, exactly there, because you have no choice. So this liquid plus A doesn't have 2 degrees of freedom. After fixing pressure, 1 degrees of freedom available in the form of either temperature or XB. If it is temperature, then XB will be automatically determined from the temperature corresponding to the temperature. This. If it is XB, it will be determined. This is the question. Okay. So, but then question dimension. Why sir it is 2 dimension? Looks like 2 dimension, but after fixing it is only 1 degrees of freedom. This is very clever. This is actually, I should say, it is puzzling. This is puzzling. So follow, I will explain this. So let me complete this T or XB. Suppose, as I have said already, suppose T is arbitrarily fixed at T1 here, T1, the XB value, the XB means composition, XB value, composition is either XB or XA, and they are related. XB is 1 minus XA, no problem. XB value is dependently, underlined, is dependently no freedom, automatically as if, and this is arbitrarily means independently, is dependently fixed at where corresponding to this temperature. What is the fixed? XB1, I mentioned here, XB1 means this is the composition from which, if you ask me, and XA is what? And XA you know very well. X is the binary system. XA is 1 minus XB and 1 minus XB1, and this is known as XA1. No problem. So you know the full composition. Okay. So this is okay, XB1. Now, as I told you, from the dimension point of view, looking from the different outlook, different viewpoint, that is dimension. And there is the challenge, there is the puzzle. From the, so let us mention, from the dimension point of view, F is 1. This represented liquid plus A. F is 1 after originally 2, but after fixing pressure, taking into account the pressure fixation, 1. So 1 freedom, but apparently or mistakenly we see this is a 2 dimension because it is a area. Okay, area over which liquid plus A exists, stable domain, surface. From dimension point of view, F is 1. F is 1, remember, should be represented by a represented as a curve. As a curve, one dimension should be curve. Why actually area? This area, okay, should be a curve. As a curve. However, the stability of L plus A solid, stability of L plus A solid is apparently enclosed in an area bound by the lines, three lines. What are the lines? Tell me, lines here. This one lines are which one? This SC, C and A. Here you have liquid plus A in this area. Apparently looks. This is that is actually a difficulty here. Okay, that is actually misconception here. By the lines is area by the lines. Which lines? A, SC, AE, AE, lowercase AE, CE and AE, SC and AE. AE, SC, AE, AC and C. Whatever area or an area. C. Okay, very good. Actually, a mixture of, I say, you know what I say, you know, this place in the diagram, where liquid plus A I have written, or for that matter, liquid plus B I have written, is a hallucination. You know hallucination? Hallucination, okay, means paradoxical, means puzzling, means fake, myth. Nothing ever exists here. So I have placed my point here. Nothing ever exists here. It is written liquid plus A. No, nothing ever exists. What will happen according to the equilibrium? If you have a mixture of liquid plus A and keep it here, what will happen, you know? It will split. It will split into here, into this side liquid, draw horizontal line. Hit this line, the liquid, and this side A, pure. So liquid is here. So similarly here if you write, take a liquid plus A here, it will split to this liquid horizontal line, liquid A. Or here, liquid A. So liquids are actually arranged along this curve, not split into this. We apply this point for different purpose. To know this is called actually gross composition, gross mathematical composition. Actually, liquid composition is here and A composition is here, which is pure A. Mole fraction X is 1. Nothing here. This gross mathematical composition, which is required to find the relative amount of liquid and solid by lever rule. That is a different story. So nothing ever exists. So you see liquid, they split. So liquid phases will be arranged along this curve, one dimension. And simultaneously solid will be arranged along the AC curve. So liquid will be arranged along this curve is AE and solid AE. So since this is, they are arranged, they are aligned along a line which is one dimension, justifies this one. This is the answer. So what I said, nothing ever exists here. The two-phase mixture, here, nothing. Any liquid plus A will split into two. I said hallucination. It looks like, apparently. No. Finally, it is. This will justify why degree of freedom is 1, and liquid composition are aligned along this line, along a curve, means at this curve, AE, and likewise solid also this curve. So this is careful. Actually, a mixture of L plus A solid when left in the stated area, when left or kept, you may write kept, when kept in the stated area, anywhere in the area, anywhere in the stated area, okay, it immediately splits. It immediately or eventually, because it is equilibrium, it takes time to attain equilibrium. These are the equilibrium. This is not an equilibrium combination. Okay, so they will split, will separate it. Liquid this side, A this side. So eventually or immediately, depending upon the kinetics, that is a different issue. So it immediately, no problem, it immediately splits into two separate phases, liquid and a solid. What will happen to this? The phase L is aligned along the curve, the line AE, and the phase A solid is aligned along the line AC solid here. Okay, this is solid. This is 0. This is A along the line AC. Because the line is How many dimension a line? One dimension. Because a line is one dimensional. A being one is apt, suitable, or acceptable, or it's apt means okay, it is okay. It is actually a being apt is correct, actually justified. A being apt, one is apt. One means, remember, originally two, but after pressure fixation it is one. So one spread over this, so justified. So final line. So we are happy. Next, take our third case and last case. So I repeat here. I have already said. Remember, wanting the understood. Like I should not waste time. Let us see C. C is what? Liquid phase. You see, liquid AB, liquid AB together. Liquid of this liquid here, A here, B there. Or say see this way, liquid here, here to this point, liquid, and A plus B also here. So three together. So two phase, three phase. First case was single phase, liquid alone. Liquid phase plus A solid plus B solid. We again start this way. Remove this. These are all over. Start. F is what? Tell me. C minus P plus 2. C is the two component. How many phases? 1, 2, 3. Liquid phase and two solids. Which is 1. Right here, P is 3. Why? P is 3 because two liquids. One liquid, two solids. Okay, so 1 degree of freedom. So start 1. So I have already fixed 1, already consumed, expended 1 pressure. So no freedom further. Means automatic, all will be automatically. Your choice is over with fixation of pressure. What? Automatic, which are that value? Means which are left after pressure is okay. Temperature composition. What is the answer? This is the only temperature. T called T, the eutectic temperature. And what is the composition? 1 by 1, 3 phases. Liquid has this composition only. It cannot be shifted to the smallest extent. Fixed. No freedom. No freedom. Rigid. Will not tolerate even a slight departure. That is real sign of no freedom. And when you have a part freedom, means to a certain extent you can remove, means full freedom, mathematically full. So 3 phases composition. Liquid fixed. This is called eutectic composition. Eutectic liquid. And what other? A solid, this side. This is like before, A solid, B solid. By D. D composition, D means pure B. A solid, pure A solid, this side. By C and D. Liquid composition here, E, solid C, composition given by point C, which is X is 1, and solid B is given by point D, which is XB is 1. So all answer. Then again confusion. Again puzzle. What is this? Or say, what is this actually? Paradoxical is what? Sir, it is so after 1 fixed, what is? No freedom, 0 freedom. So automatically fixed. But looks like a line, sir. line. Line is one dimension. They are aligned here. Again, previously it looked like 2, but actually it was found on scrutiny 1. Here also you see looks like 1, a line, but it's a point. 0 dimension and hence 0 freedom. That will be explained. Few lines, okay? That will be see. See, you try to think yourself. See this. Again, I tell you, it has no meaning. Again, this between C and E, no meaning. C is meaningful and E is meaningful and D is meaningful. But between C and E, nothing ever exists. No mixture. Liquid plus A doesn't exist. Liquid will be here. Again, A will be here. So, liquid will be this point, a solid, this C, point, 0 dimension. Or say complete this. Here between E and D, nothing ever exists here between this. Liquid will be here. Again, if you have any, it will split. Liquid here will be tied here and B at D means pure B. So nothing ever exists. So what remains? This point, liquid for liquid composition. Liquid with this composition given by the point E, and solid B, this composition XB is 1 at point D. Point means 0 dimension. Dimension point of view 0, and it makes sense that it is 0 degree of freedom. After 1 has already been taken away. Originally 1 taken away in the form of pressure, so 0 justification. So I am writing this after fixing the value of P, the remaining degrees of freedom is what? 1 minus 1 is 0. The temperature and 0 means automatically. The temperature and composition of the phases composition of the phases, temperature and composition of the phases are automatically, you may use this, are automatically fixed. E.g., for example, here in this case, tell me, e.g., T is what value? Automatically, T is T. It cannot be any other. It cannot be any other. T. None. Only T. Not this, nothing. Not a bit. Greater or smaller. T is T, which is popularly known as eutectic temperature. Is T, and composition of the liquid phase is given by point, what point? E, which is known as eutectic point, which is known as eutectic point. And of course solid A and solid B are pure. So anyway, but the next question comes from the dimension point of view. From the dimension point of view, AP is 0 should be represented by a point. However, apparently the three phases that we are discussing, the three phases, liquid A and B, liquid A solid and B solid. What are the liquid A and B, the three phases align along the line. Align looks like the here. The line looks like an impression of line, means one dimension against expected zero dimension, 0 degrees of freedom. It is one dimension contrasted against 0 freedom, incompatible. But then we understand the real story. Actually, line does not exist. Actually, line is okay. They are actually compositions are given by the points only. So this I write liquid A and B, as I have already said, align along the line CED. Is okay to? So everything? Here also is okay. This one is C observable, visible?
Yes. Upper one visible, yes.
Along the, thank you. Align along the line CED. CED. The contradiction, one line means one dimension. As I have already said, so it may be noted that no phase mixture ever exists between C and E. Between C and E, like here. They will split. Phase mixture like liquid plus A. It will go to the split in the form of liquid with this composition, A with this composition. And they will be like this. Here. So capital, then they split. Liquid, this side A. Liquid A. Here inside between liquid and A, nothing. As I have already told you, so ever exists between C and E, likewise between E and D, same liquid plus B. So liquid, nothing ever exists. Okay. So exists between C and E, and between and between E and D. Here also same thing, liquid, anything brought here will be liquid, liquid here, liquid B, liquid B. So this line has no relevance, has no existence in a sense. Okay, means, so there will be, so 3 points. Okay, you see, okay, you know already I have discussed between E and D. Solid A occurs, solid A occurs at the composition given by solid A given by point C, point 0 dimension given by point C, liquid phase occurs at the composition given by point E, liquid here, liquid E, and solid B occurs at the composition given by point, what point? D. So given by D, because a point is 0 dimensional, see F is 0, it is in agreement, F is 0, okay. So 0 dimension and degree of freedom is 0, okay. The available degree of freedom means after we have fixed the pressure. I originally 1, but after utilization of 1 degree of freedom it is 0, so 0 and point which is 0 dimension are compatible, are in agreement. 0 is 0 dimensional, because the point is 0 dimensional, F being 0, is apt. F being 0 is apt, means as I told you, it is suitable, okay, is correct, justified. F being apt is apt, okay, suitable. Being 0, F being 0 is apt. So with this we have finished the 3 cases, okay. So you may draw a line here. So 12 examples. So these examples, 12th example is finished. So 12 examples, all 12 examples are over. Okay, demonstration with 12 examples are over. So we'll take up now the new topic under the Gibbs phase rule, that is construction of stability diagram. Shall I remove this? So this I remove this. This part is over. So next topic. Construction of stability diagram. Stability diagrams. Six examples. Six examples. Six. Okay, today I start the first one. System NO, metal oxygen. So here you will learn how to construct the diagram. Means you will not borrow from books. You will draw yourself, or you will not use software. If it is complicated or maybe lengthy, then a different issue. But first of all, you learn the simple diagram. This is the first one, MO. You will learn how to draw the diagram. Then you will take help of for shortage of time or for saving time, or otherwise do that. But beforehand, you do yourself. In fact, you should try yourself first. Then you have a comment of the diagram. You have a full comment on the diagram. You can answer many other questions. Only the diagram, just drawing the diagram and having the diagram is not enough. So if you ask questions from the diagram, then what will you answer? Many questions can be answered. Many questions can be asked. That is the problem. Students are using softwares like say Faxage, and I used actually one for my students Solver. But I always try to draw the diagram myself. Okay, so you should learn how to draw this diagram. This will be instructed. Okay, here in this course and under this topic. Okay, the construction of stability diagram. 6 examples will take one by one. I have referred to some of them previously when 12 examples I discussed. Remember, so iron, iron silicon oxygen, iron silicon oxygen. Okay, one system. Okay, FeO, write this. Okay, no, I'm sorry, iron manganese oxygen one. Another is lead silicon oxygen, lead oxide, lead silicon oxygen, or like this. Okay, this I took actually, this one. And third, maybe another example I give you actually. What is this? Such examples I suggested. These actually they will be taken up later, subsequently, now the time actually. Okay, what else actually? What are the other diagrams? I just let me think. What is this? Oh, iron carbon oxygen. This will be taken up now, one by one. Follow me and activate. So I will start with this system MO involving M solid, M liquid, MO the oxide, solid, MO oxide, liquid, and the gas phase. And the gas phase. And the gas phase which contains only oxygen. This is the topic, system memo, and this is the diagram. Figure 1A I have written. No, I am very sorry. It cannot be 1A. Yes, 1A. One for some reasons it will be 1B. Okay. So I am done with all these things. So maybe there is a reason. This is over. It is better I remove this. Otherwise, it may distract you. So no reason. This is all over. This is the diagram. I've drawn this. I've shown how it is drawn. I will actually explain you, and this will be the diagram. And there is actually stable line, metastable line. This discussion is very important, and identification of stable line and metastable line, etc., etc. There are things. This will be coming into picture. So remember, these phases will be stability domain of these phases. Metal solid should be shown in the diagram. Metal liquid will be shown in the diagram. Metal oxide solid will be shown in the diagram. Metal oxide liquid will be shown in the diagram. And the gas phase always be there, oxygen. Because O means gas in the form of O is actually will be present in the form of a gas, oxygen. So I have drawn this. I tell you in nutshell what I have done. This is the diagram. Sorry, this is the diagram. Okay, log ln PO2 versus 1/T plot. We'll start with the phase rule. Gibbs phase rule. We start. This follow me. Okay, very interesting. When you learn how to draw this diagram, then you will actually feel yourself actually satisfied, and you will be very satisfied, and you feel yourself actually enriched. Follow this. I am showing you answer. I am giving you at the beginning. Plotting ln PO2 against 1/T. This is the diagram. This dotted line for construction lines. They should be removed. I have not removed, but when these explanations are all given and okay, the equations are written and equation for different curves are given. Then at the end, these dotted are metastable lines. Okay, they will not be seen in the diagram. So then I will remove this. If I strike them off, and then actually what I will do, remove them from the figure. Then you have this diagram. You see, showing metal solid stability field. See, MS, metal solid. See, metal liquid stability. This is this one, this space. This region, metal liquid stability field. This is metal solid. This is what? This whole metal oxide solid. These are written, okay, don't worry. These are construction, about construction. And this is what? Metal oxide liquid. So 4 already there. And gas phase is showing on the y-axis. ln PO2. The gas phase and its partial pressure value is given on the y-axis, so no problem. Everything is okay. So let us start. Okay, start. How we start, you know? Start this way. I say start this way. Which way you will start? I tell you what, this is kind of design, planning. Planning is what? How many variables I have to display on the diagram, etc., etc. Do I have to fix any value? Like this pressure is constant. So, do I have to fix any value before the diagram drawn? Or under the condition, under the stipulation of that fixed pressure, the diagram will be drawn? Under the condition that pressure, fixed pressure value, the diagram will be drawn, or temperature, for example, not pressure, say temperature. It may be temperature also, temperature. These questions will be answered from this consideration as I write now. You will say maximum how many F max, F is the degree of freedom, how many maximum variable you have to handle. Accordingly, suppose it is 2, then 2-dimensional drawing will be good. Maximum. Maximum, why maximum? F we know, A max is nothing but C minus P minimum. It is maximum when P is minimum. Minimum number of phases I have to consider. I have to come across. Minimum number plus 2. What is P minimum? Here in the present case, P minimum is what? I am writing for you. C is a two-component system, metal, oxygen, element, NO. So 2 component. Minimum phase is also 2. I am showing you how. Plus 2 is 2. Why it is explained? C is 2 1 by 1. C is 2 why? Which are they? Metal, N and O. Answer. P minimum phase. P minimum is what? Minimum phase is what? Now, one condensed phase would be there. Say one condensed phase. Condensed phases, solid or liquid, M or MO, whatever. Minimum. At least one condensed phase. And gas phase is inescapable. That will be always there. So, is what? P minimum is 2. So, write this is 2. P min means P minimum right here. P minimum. Max is what? Max is maximum. A maximum corresponds to P minimum. P minimum is what? One solid phase is stability field. So the diagram just have a feeling. Oh, it can be together. But minimum. Metal solid. Two together can be 3 together. Along this curve, 2 together. Metal solid and metal oxide. And at this point, 3 together. Metal solid, metal liquid, metal oxide. But this is not minimum. This is not P minimum. Minimum is what? One of them. These one, metal solid. But and gas phase on the y-axis, it is always there. Some value always there. So gas phase. So minimum is what? Is 2. P minimum is 2. One condensed phase. Condensed what? Solid or liquid? One condensed phase. Plus one gas phase. What is the high gas phase? Because oxygen is there. Oxygen will always be present in form of oxygen. Okay, alone or in combination. So here, since there is no other, like such other elements like carbon, sulfur, etc., is not present. So chlorine, etc. So oxygen will be in the form of oxygen gas. Okay, one gas phase. Why? Since the reason is this. Why one gas phase? Since O is present. This issue. Since O is present, so it will appear as gas phase. Okay. In the condensed phase also MO, oxygen is present, but gas phase it will also be. It must be present, and that should be considered minimum number of phases. One gas phase, one condensed phase. So total is 2. So this is, you can give it another bracket. Sorry. It's okay. So this explains. So 2, maximum 2. So maximum 2, which are actually considered here, maximum 2. So a 2-dimensional plot, follow me. Since 2, a 2-dimensional plot will be good enough. Will be capable of presenting these phases. alone or in combination, along with the gas phase. Whole diagram, in short, the stability diagram can be drawn by two variables in two dimension. What are the dimensions? What are the two variables you have considered in this two dimension plot? ln PO2 in the form of ln PO2. For some reasons I will explain. You know perhaps. Remember ln PO2, and T in the form of 1 by T, because for the same reason, because they will connect the delta H0 enthalpy. This you know, ln K and 1 by T, that relationship. You have already used this metal oxygen stability, this example, 12 examples that I have discussed, never forget. So they will be actually, those concepts will be used here. So very good. So a two-dimensional plot, since it is two, a two-dimensional plot can be made without having to fix any variable beforehand. Nothing is to be fixed before, like pressure I fixed in the phase diagram, binary phase diagram. Here I have not fixed anything, because only two, no problem, 2L plot, 2L use, two variables. So since it is two, but when we have to, can without having to fix any variable, when we will require to fix any variable? Yes, we will require. When? I tell you, if F max happens to be 3, we'll come across with this situation later, not this first problem. No. First example, later. 3, F max is 3, then what will do? 3-dimensional plot we have to do. We have to make. No, this we want to avoid. We don't like that. 3-dimensional possible, but we don't like that. We do what? We fix one value. Like say temperature is fixed. Just 700 Kelvin. The moment 1 is fixed, now how many remaining? 2. And 2 will be shown in a 2-dimensional plot. Wow, how much time left?
1 hour 57 minutes gone. 3 minutes left. 2 minutes.
I will finish in time. Okay.
In time.
You come. 1 or 2 minutes maybe at the most. So a 2-dimensional plot. So if it is 3, then no, then 3-dimensional I kind of want to avoid. So what we'll do? We'll fix one. The moment one is, the diagram will drawn for a fixed temperature. Then it is 2 remaining to plot in the 2 dimension. Meaning on a paper, on a piece of paper, 2 dimension. So this is the state. To illustrate variable beforehand. This is the meaning of this. So without having to fix anything, we can draw. In this case, since F max is 2. So to illustrate, as I have said here, to illustrate, if you have difficulty, if F max was 3, we had to fix one variable. We had to fix one variable and plot 2 variables and plot the remaining 2 variables. That's right. That's right. So this is the discussion. The initial design, planning. You're planning about this. Next is what? So let us start. Since we have already seen it is 2, so let us. So what are the? This will be treated. This will be in the axis. they will be represented, they will be shown in the axis, these two values, F max is 2. Which are these? Here, ln PO2 and 1 by 2. So this is mentioned now. Let us consider the variable chosen for the two-dimensional plot So in continuation, I tell you, suppose a max was 4, is 4, what will you do? It cannot be, it is 4 dimension. So how will you reduce this number? Fix 2 of them, so that 2 remains. These 2 remaining ones will be plotted in a 2-dimensional as a 2-dimensional plot, 2-dimensional diagram on a piece of paper. So it is since okay, this is simple now because it is 2 only, so nothing has to be specified beforehand. Just freely. So 2-dimensional, let the variable chosen for the 2-dimensional plot are of the current system, plot of the current system. What is the current system? System MO are ln PO2 and 1 by T. And 1 by T, as you see here, 1 by T, ln PO2 and 1 by T. So why not? Why not? Question comes. Always question comes. Why not PO2 and why not T? Yes, that is possible. Only thing is this you will not get these nice straight lines. Linear relation you will not get. What you get? Non-linear curves. We actually prefer linear curves. Of course, sometimes you have to consider also alternatively we consider non-linear also. That is possible. That is possible. That is very much possible. Okay, but it is preferred actually to have, if possible, linear presentation. Okay, so all curves are straight lines. So you note this point. If it was T versus PO2, the curves generated would be what? Non-linear. Would be non-linear. To produce a linear curve, Papa, 1 or 2 minutes. How many minutes? Past?
4 minutes past.
4 minutes, 1 or 2 minutes, okay? To produce a linear curve, ln PO2 versus 1 by T plot is required. 1 by T plot is required. As will be explained subsequently. As will be explained explained subsequently. Subsequently, the complete, after all this construction, the construction I will give you, the complete diagram is here. That is figure 1A. Stability caption is what? Stability diagram for the system MO. Stability diagram. This full diagram is there. We'll actually explain. We'll keep on constructing line by line, and look at this is so the complete stability diagram. Complete stability diagram is shown in figure 1A. Is shown in figure 1A. Okay, complete diagram. Okay, so now actually we will start construction of the diagram. Now the real method or procedure. Okay, construction. So with the heading construction of the diagram. First number of lines. There are a number of lines are there. So this we'll take up one by one. The first one is consider the equilibrium involving M solid and MO solid and the gas phase. Which contains oxygen only and the gas phase, oxygen. In the form what? What is the reaction equilibrium? You know very well. M solid plus half O2 gas goes to MO solid. Call it equation 1. So we'll stop today here. Okay. This is will actually to continue in the next class to continue in this. So this is actually this equilibrium will be shown by a line, by a curve. This will be discussed next class. Thank you very much for your patience and for your energy and for your cooperation, for your interest. Thank you very much. See you next class. Bye.